Hello, everyone, and welcome to another wonderful week in industrial chemistry. So far we've been mostly talking about ideas such as uh, how I can design and operate a industrial chemistry process. One of the things I want you to be aware of, because this is actually quite a large part of a lot of chemical engineering courses, is going to be things like cost estimating and trying to um, evaluate a chemical plant more from a money perspective. Because if you're going into industry, you better know it's all about the green. So, one of the big things we need to first acknowledge is that a chemical industry a plant or a chemical plant needs to make money. So, they won't approve any plant unless you can know it can turn a profit. This is going to essentially focus in on several key issues. The first of which is going to be costs and profits. So, these are going to be a lot of what we're talking about today. But we also have to acknowledge that if I have too high of safety risks, this can also bring up a lot of liability issues, which means it does have its own monetary impact. If a process is too dangerous, I'm probably going to avoid it. Similar things go with environmental impacts. I hate to be cynical, but it turns out that a lot of environmental impacts are going to be evaluated also based on their potential monetary impacts. So one of the first things I need to consider when looking at a chemical plant is going to be how much money I'm going to need to spend. And so we're going to be focusing on how we can divide up various costs for building a plant. And it turns out that a lot of our costs are going to fall into two major categories. Operating costs, which is essentially going to be how much money does it take to operate a plant on, say, an annual basis. The second which is the one we're going to talk about first, is this idea of capital costs. So capital is going to be all of the costs involved in building a chemical plant, but also operating it until it starts a profit, till it turns a profit. So one of the things you have to watch out for is that a lot of people put aside enough money to build a business, but not enough money to wait it out until all of those debts have been paid off. And and this second category can really break a lot of groups. And as such, we can divide our costs into two major features. The first is going to be our fixed capital cost. And this is essentially just the building and readying the chemical plant until I can start operating. And then I have to worry about the working capital. So again, how much money do I need to set aside to operate the plant until my profits have finally caught up to pay off not only my fixed capital, but also caught up to the working capital. And these sort of estimates can get a little bit tricky. But in general, one of the big things you should kind of be aware of is that it's pretty common for a working capital to be up to about 30% of the fixed capital costs. There's going to be a lot of factors that are going to control our working capital costs, including all of the factors that we'll talk about later going into operating costs, but also the relatively how expensive the plant is. If I have a cheaper plant, it's going to take me less time to pay it off. The larger my fixed capital cost, by logical extension, so will be the larger. I'll also end up with a much larger working capital. So let's go ahead and start off with this key controlling factor, the fixed capital cost. And we can actually split this up into a lot of subcategories. So the ones you might be, the first one we should make sure to talk about is the actual design costs. Because it turns out if you need to build a chemical plant, you have to often pay a lot of chemical engineers and architects and civil engineers to actually design the plant. And all of that time can cost a lot of money, especially to make sure that the whole system will be able to maintain reasonable operations. Then we have to purchase and install all of the equipment that we need. And this isn't going to just be the major pieces of equipment like our big reactors. It's also going to be smaller pieces of equipment like piping, um, quality control instrumentation, control systems, temperature regulators, heat exchangers, valves, uh, backups and redundancies to help prevent any catastrophic issues. So there's a lot more equipment involved than you might think at first glance. And then not only do I have all this various equipment and a building to put it in, I also have to have not only the building I put this in, but I also need all sorts of support structures. So the simplest one you're probably going to need to account for is storage space. Now, this might be pretty simple if I'm making something like soap, but this can actually be quite extensive if I'm, say, in an oil refinery and I need a place to store a couple million barrels of crude. Can be a bit tricky. But we also have auxiliary services, which is almost a special category of support structures. And this is going to be especially things like utilities. So this can get into support structures if you're required to have on-site power generation or water purification, which is not uncommon. But also, I need to make sure that I have any other important features, such as maybe simply Wi-Fi if I've got a lot of smart devices and controls on all my piping. And it turns out that most people don't like working in a nice solid steel or concrete building. So you have things like landscaping, parking, and the like. As well as one of the other things you might have to watch out for is things like security, depending on what chemicals you're making. A little bit problematic. So I need a good way to try and estimate some of these capital costs. So the easiest approach I can take is to try and find an existing chemical plant that somebody's already made and just make an exact copy of that and adjust for inflation. So one of the nice things about adjustment for inflation is, as many of you are aware, you do have to watch out for the fact that different fields, different parts of the economy will have different rates of inflation. A lot of it in both everyday life and in chemical engineering will often be tied to the cost of oil, but some things may see greater or lesser increase. Thankfully, chemical engineering textbooks have a lot of good indexes that are specifically designed for cost just for chemical engineering. These include such things as overall plant cost indexes, usually provided by year, but you can also have itemized costs, which look at the inflation rates for individual things such as machinery, structural supports, labor in several different categories, and buildings. So using these itemized or overall costs, usually you can get a pretty good idea of how much it may take to build a new plant. But one of the things is that I might not want to build the exact same plant. I may want to scale it up or scale it down depending on how much chemical products I want to generate. So it turns out there's an equation for this too. So what we can end up doing is generate a cost adjusted form where C2 is essentially the cost of the new species, C1 is the old, and then we're going to be looking at the relative operating capacities. So S2 is essentially the operating capacity of the plant you want to build, and S1 is the operating capacity of the plant that you're comparing to. N is going to be more of a general scaling parameter, and it's generally taken to be 0.6 unless you have information about scaling for the specific type of plant that you're looking at. So it's a pretty good rough estimate. Now, this actually has some really interesting implications. The first of which is going to be the fact that if I want to build a plant with double the capacity, it turns out I might not end up having to pay twice the cost to build it. So let's go ahead and run our equation. So I'm going to find the cost ratio of doubling my capacity and using a classic n of 0.6. Now, if I do this, I'm going to find my cost ratio to be 1.52. So this means that even though I'm generating a plant that produces twice as much, I only have to pay 50% more. And this turns out to be one of the reasons why a lot of chemical plants tend to go big or go home. So as long as there's going to be a sufficient market for the chemical that you're producing, you may as well build a larger capacity. However, don't forget, you also need to account for inflation, and this can be another limiting factor of just simply how much capital I can raise to help pay off the plant, and if inflation makes this cost ratio a little bit greater than I'd like. However, it turns out I can't always base an estimate on a previous plant. So in these cases, I often need a little bit more of an itemized estimate. And for this, we use a special equation where we find our fixed capital costs. So again, this is how much it takes to get the plant operating, based on all of the equipment cost I need. And then we adjust it with what's called a laying factor. And it turns out that this laying factor is going to be a little bit different for different types of processes. Generally, it's going to be about 3 for solids, 3.6 for solids and fluids, whether this is a gas or a liquid, and about and almost 5 if it's just for fluids. So one of the real questions that this should raise is, why is it that fluid processing is a lot more expensive? And simply put, you have to build in a lot more pipes. When you tend to just be working with solids or some solids and some liquids, this tends to be a little bit cheaper because I don't need to have quite as rigorous chemical transport networks, and that I can be a little bit more lax on some of my building considerations. So again, this is one of those things you should watch out for. But I also want to drive the point home the point that it turns out that our fixed cost can be anywhere in between 3 to 5 times as much as just the equipment costs alone. So while equipment costs are going to be a good resource for trying to estimate our overall cost, it turns out there's a lot more factors that are covered by this laying factor. And some of them can be a little bit surprising. So one of the more surprising ones for traditional chemists like us is going to be what's called indirect costs. So these are things that I can't just point to and say, hey, look, I bought that. So we already brought up a couple of these. First and foremost is going to be this idea of design and engineering. I have to pay a lot of people to help me design my plant. And it turns out that this can be about 20 or 30% of 20 or 30% of essentially what are going to be my tangible costs or direct capital costs. So fairly high. We're also going to need to hire somebody to go out and get price estimates and make sure we get the best bang for our buck on all of our equipment. And it turns out that that alone can rank up to about 2% of our overall capital costs. Then don't forget, we also need to pay off some contractors to help build the whole thing. And that can be about 5 or 10% of my direct capital costs, as well as always account for something going wrong, which is about 5 to 10% of our overall costs. So always build in a little bit of that buffer. And again, when we add all of these up, it turns out that things that I can't point to, hey, look what I bought, end up about 50% of our direct capital costs, or you can think about it as about a third of our overall costs, fixed capital costs. But since we are comparing everything to direct capital costs, let's go ahead and talk about that. So this is essentially going to be the purchasing and installation of all of the physical components. So this is stuff that I can say, hey, look, I bought that, or okay, I bought that and had it installed. And things like buildings can quite add up. So let's go ahead and look at some of the individual ideas of this. So of course, we need to buy a building and we need to go ahead and prep it. So this might be, say, demolishing what was previously there, or just leveling the ground, or potentially just digging a whole bunch of trenches for to lay down water lines. Because don't forget, with a lot of chemical plants, you're going to need a lot of water. Then we, of course, need all of our buildings. And this isn't just going to be for the chemical plant itself, but it's also going to be offices for people to work, workshops for people to work on the equipment, because you're going to need to fix something sooner or later, and laboratory space. If nothing else, if even if you aren't doing any sort of development at your plant, you're still going to need some lab space for quality control. Then, of course, there's the classic equipment. And don't forget, we need piping and storage for both our precursors and our products. But it turns out that if everything isn't on a continuous flow, we're often going to need space for intermediates. And even if the whole process is on is run on a continuous basis, you need to have some sort of extra storage space in case you have to shut the process down. And then, of course, don't forget utilities. And the utility requirements for a chemical plant, as we've talked about in our energy balance, can be quite extensive. So now we've been comparing a lot of our estimates based on equipment costs. So let's get a little bit more into details on these, because this is really what we're factoring on. And as you saw, they can be somewhere in between about 20 to 30% of our overall costs. So turns out the only true way to know our potential cost of a piece of equipment is to actually kind of go out and do those estimates and buy it, which is one of the reasons why that's about 2% of our direct capital costs. But it turns out you can get a rough idea of what you're going to need to pay for by using a lot of books and professional journals. And the Industrial Chemical Engineering Society is actually quite good at providing a lot of these. But it turns out that I even have a couple of industrial chemistry books, which gives you a rough idea of some of the general prices for, say, some reactors. So here's some batch reactors, which, don't forget, can also be run as CSDRs in 2004. However, if you want to adjust that to more modern notation, the cost index going from 2004 to 2016 is about 1.3. So again, up these guys by about 30%. So if I want to build in a small reactor, notice that the smallest reactor here is still on the 5-gallon scale, which is much larger than we're used to in our labs. I'm paying about $30,000, but I only have to pay about $9,000 more to go up by an order of magnitude. And okay, if I go up to 500 gallons, I have to double that price. But notice, going from 5 gallons to 500 gallons, I'm still paying only a little bit more than twice as much. And by the time that I get up all the way to 8,000 gallons, I'm only paying about 10 times as much as I am for a 5-gallon reactor. So it turns out that this is going to have some real serious implications for trying to determine scaling, because it only costs me a little bit more to have a lot greater volume. But then you have to ask exactly what sort of advantages are you going to end up having from this greater volume, and what sort of additional support features will you need, such as simple things like laboratory space. But one of those things that you really should watch out for, and again, another driving feature of why scaling up a plant to a larger size is often cost effective. So one of the other things you have to watch out for is going to be what material I'm going to make all of my equipment out of. And so, for example, I have some cost estimates uh, for some heat exchangers. So we talked a lot about heat exchangers last week. So let's go ahead and take a look at the idea of what materials I can make them out of. So I can make them out of carbon steel with brass, carbon steel with stainless steel, or just all stainless steel. And this is going to have a serious effect on cost. So carbon steel is going to be rather cheap, whereas I can be paying a significant amount more as I start going to more durable materials like brass or stainless steel. But I might need this for chemical resistivity, which I'm going to talk a little bit more about later. But one of the other important things uh, that I really want to help drive home is this idea that as my heat transfer area goes up, I'm my cost is going to be significantly increasing. But it turns out that say if I'm going from a heat transfer area of 10 to 100, I still don't see that same factor of 10 increase in the cost of that same heat exchanger. So again, a lot of the costs are going to go into uh, making the piece of equipment that I actually want, and I often get reduced costs for scaling. So in general, if you have to choose in between one large heat exchanger or several small, cost will tend to go towards one large heat exchanger. But as we've seen uh, before with the idea of multiple reactors, there can be some serious advantages of breaking up into smaller heat exchangers. But again, you often need to do the math to evaluate which one's going to be cheaper in the long run. Now, again, we see a lot of differences based on cost as well, where you can be easily paying several times as much for a stainless steel heat exchanger as a carbon steel material. So the real question is going to end up being about why. And so when I'm going to be choosing a material, we've got five major questions I should ask myself about. The first of which is going to be the cost and the availability. So as we've seen before, a lot of higher end materials are going to end up costing more. And it turns out that you simply may not be able to get any type of piece of equipment in any type of material. For example, I just might not be able to find a titanium heat exchanger. Just might not be there. You also want to be very aware of what sort of techniques you're going to need to use for the installation. It turns out that some very durable or cheap materials are not exactly that great at welding, and some can't be cast at all. So think very carefully about what sort of physical manipulation you're going to need to perform upon the material you're looking at. And we have a whole variety of mechanical properties, each of which is going to dictate the durability of the material to uh, certain external effects. So, for example, you have to worry about tensile strength, or how easy it is to stretch out the material, which can be very important when you're applying serious internal pressures to, say, piping. The stiffness, which is going to be related, is how easy it is going to be for the material to expand. You have to watch out for the fact that stiffness can often be reinterpreted as brittleness, and that's going to be associated with the relationship of stiffness and toughness, how hard it is to break, and actual hardness of how hard it is to etch. But again, one of the big things we're going to be looking at for is fatigue and creep resistance. So essentially, how quickly can the material wear out? And turns out effects of temperature can often make some of these materials quite brittle. But the one we typically talk about the most is going to be corrosion resistance. And it's worth noting that corrosion comes in many different features. So first, we have things like uniform corrosion. And so this is just uniform wear of how quickly, so how much thinner will the material get in any given over a certain period of exposure. This is going to be slightly related to this idea of pitting, and pitting is often going to be driven by um, by impacts by small materials in my reactor. And as we talked about, when you're dealing with things like fluidized bed reactors, where I'm shooting high pressurized catalyst all over the system, pitting can be something you really need to watch out for. And then you've got something called erosion corrosion. So erosion corrosion is essentially a combined process of I may have some sort of pitting, and then I'm going to see some erosion around that pitting site. So the erosion corrosion process can be a little bit more finicky. Then we have classic oxidation, and so oxidation can take place uh, from many different sources, including, say, just oxygen, but it can also get a little bit and is typically something you have to watch out the most for when you're dealing with metals, because it turns out that metals can easily oxidize from the metallic form to the metal oxide, like our good old friends, aluminum oxide and rust. And then one of the last things you have to watch out for is, again, going to be this idea of galvanic corrosion. And galvanic corrosion is often presented when you have a combination of different materials present in either a reactor or at different points along a pipe, where my two different materials have different reduction potentials. So I'm going to see corrosion at one point along my pipe, and I'm going to see buildup of oxides usually along another portion. So this can be quite a problem to watch out for. And again, the last major feature we need to watch out for is going to be things like electrical properties, because it turns out that we don't always want our pipes to be able to conduct electricity, especially because there may be things like static buildup as I'm sending lots of fine materials like sand or catalyst particles across a surface. So watch out for that one. But again, there's our good old friend chemical reactivity. The one you should most specifically watch out for is a lot of industrial chemical processes make use of things like amines. Turns out that amines are very good ligands. So if you're using a lot of amines, you have to watch out about using any metals, because it turns out that you can actually leach away all of the metal from your tubes. So this is a very common driver of corrosion. So again, be very cautious with making sure that the reactivity of your material will match up with the reactivity of whatever chemical you're using. Because again, this can be a big driver of corrosion. So this is actually a picture of a real lab that I've worked in, where they have HCl baths to go ahead and clean off their glassware. All of this equipment was newly installed within a year. So 1 year after installation, just with an open bath of HCl present near this equipment. And this is what your materials can look like if you choose a cheaper material instead of one that's going to be acid resistant. So this is one of the reasons why material choice can be very important. So I'm going to quickly walk us through several of the most common materials that you're going to see used in a lab setting. It is worth noting, if you want to get a good idea of the reactivity and stability of a wider range of materials, I put several resources available on the Blackboard page. So our classic workhorse materials are iron and carbon steel. So carbon steel is literally just iron with some extra carbon, which makes it a little bit more durable. And the biggest advantage of these is that they are very cheap and they're very widely available. So if you don't have any special considerations, go with this one. In addition, they've got great physical properties. They're very durable. They're fairly stiff. Tensile strength is great, reasonably temperature resistant. And most of these physical properties go up significantly with the carbon content. So as I quickly go from iron to a good carbon steel. Now, one of the things you have to most often watch out for is they're very susceptible to corrosion. And their three enemies are acids, bases, and amines. So if you're going to be dealing with most aqueous solutions, you're often going to be in industrial settings, you're often going to be dealing with one of these three. So watch out for using iron and carbon steel. However, for most organic solvents, it turns out that they're fairly durable, as the polar metal surface is rather unreactive to most of the nonpolar solvents as long as there isn't any chlorinated groups. However, as it turns out that I often like to use acids and bases, one of the options I can do is to go from carbon steel to stainless steel. So depending on what your danger is, you can go with different types of stainless steel, and watch out, there are many different types. So what you're looking for is something that contains chromium if you need to resist oxidation, and if you need to resist electrochemical corrosion, such as the addition of electrolytes like salts, or if you need to resist ligation from things like amines, or just simple oxidation from acids, go with nickel steel. And this is usually the most common form you're going to find. However, one of the things that you should watch out for is that stainless steel can often be at least twice as expensive as carbon steel, and it also is a little bit more toxic to manufacture. If anyone has heard of Erin Brockovich, she was looking at chromium-6 contamination, and chromium-6 is essentially a byproduct of a lot of steel manufacture. However, sometimes our basic metals aren't exactly what we want to go for. We have to go for some things that are a little bit more exotic. So one of the good options out there is something called Monel. And this is essentially a nickel copper alloy. It's going to be a lot more expensive, but as long as I keep my temperature below about 500 degrees C, it's got great mechanical properties. And it turns out that it's almost entirely corrosion resistant. However, watch out, you may need some other materials once you get to high temperatures. But if you're looking for something that's kind of the benchmark of corrosion resistant, you're looking for Monel, and that's actually this picture here on the top. You may have mistaken it for other kinds of metals in the past. However, sometimes we want something that's nice and cheap. So plastics are the future, right? That's what everyone keeps telling me. So one of the things to note about plastics is they have much lower mechanical strengths. However, if you're not going to put it under that much pressure, it can actually be a fairly good choice. However, it's also going to be fairly limited in operating temps, as most plastics will melt once we get much above 100 degrees C, and even high temperature plastics will start giving away by the time you hit 200 or 300 degrees C, which is still in the region of a lot of chemical processes. However, they are very resistant to most acids, salts, and amines. So if you're working with amines or highly saline solutions, it's usually worth the move of going to plastics. However, make sure that you consult your corrosion tables to see what type of plastic you're using, as some plastics are going to be much more resistant to acids than others. However, if you're going to be working with organic solvents, stay far, far away from plastics, as they will very frequently melt the plastic in question. And this is almost certainly a guarantee if you're working with a chlorinated solvent. But sometimes using one of these materials might not be the right choice. So you can often look at things like protective coatings. For example, if I want the higher mechanical strengths of metals, but I want the resistance to amines of a plastic, I may look at a plastic-coated metal surface. So again, that's something to be aware of when you're looking at your choice of materials. However, all of this has been just talking about our fixed cost. I want to make sure I quickly talk about this idea of operating costs. So our operating costs are typically split into two categories. The first of which is going to be our fixed costs. So these are things that I can easily allocate a monthly or annual budget. So classic examples of this are going to be maintenance, because a lot of maintenance is going to be, I'm going to need have a regular schedule at which I'm expecting things to break. And it turns out that this can be on an annual basis about 10% of what I paid for the plan as a whole. So this one can be a big backbreaker. But as many of the recent catastrophes in the economy have shown, you also have to watch out for things like insurance. This was a big deal when Houston, which is one of the largest chemical production centers in the world, got hit by a hurricane. So make sure you have your insurance paid up. But don't forget, the only thing you can count on in life are death and taxes, and it turns out that chemical plants have to pay them too. Also, it turns out that labor costs are also fairly predictable, as you generally know what you paid for, what you're paying everyone on an annual basis. And again, this is often somewhere on that 10 to 15% of our operating costs. So again, it may not be the greatest portion of what you're paying on an annual year, but make sure that you're aware of it. However, you also need to leave some overhead for just when things go wrong. And again, this is going to be roughly on the same scale of your labor costs. However, while these are things you can annually budget for, one of the biggest banes of a chemical plant is going to be the variable operating costs. So these are things I can't predict. And one of the biggest things you have to watch out for are raw materials. So, for example, we've seen this a lot lately where chemical costs have gone up and down drastically when things like hurricanes have hit or the cost of oil has shot up or shot back down. So again, watch out for this. Watch out for what might happen with chemical costs, both your raw materials and essentially what you have stockpiled. And again, utilities are a little bit more predictable, but depending on where you are in the country, these can often vary by about 50%, especially as utilities are cost slightly different for industrial consumers than for residential. And turns out you also need to allocate for shipping, how much it costs to ship all your materials, and how much you're paying for people to go out and do sales. And watch out, R&D. You never know exactly what your researchers are going to be asking for this week. So you can usually get some rough ideas of all four of these, but it can significantly affect how much you're paying on an annual basis. And again, I do want to really emphasize that the shifting cost of your feedstocks and how much money you're making from your product materials can be the real major enemy of a lot of chemical companies. And more than one chemical company has gone out of business because they were counting on building a plant that took advantages of cheap feedstocks or expensive products. And if that market collapses, your whole plant can go out of business real quick. So that brings us to the end of cost estimations. I'll see you next time.